Good morning. I'm Jim Vaupel, and I'd like to start this meeting, the first conference of the Evolutionary Demography Society. Can you all hear me okay? Is this the right volume? Good. I'm very happy that you all came. We had a nice reception last night. Those of you who came enjoyed it very much, I think. And we have a full day today with a lot of very exciting talks. I'm going to start. I'm the first president of this society, and I'll be president through the end of this week. and then Tulja is going to take over, and he'll be the second president. And Tulja is going to arrange the next meeting of the society next November in Stanford, California. The person who more than anyone else arranged this meeting and did an awful lot of hard work to make sure it is going to be a success is Dan Levitas, who's sitting here. Would you stand up, Dan? So Dan is the secretary of the organization, and if anybody has any problems, questions, difficulties whatsoever, please talk with Dan. I'd like to get started on my talk, but is there anything that anyone would like to bring up that's important that we have to talk about before we get started? Oh, okay. Then I'm going to talk about the nature of evolutionary demography. And last night at our board meeting, Hal Caswell said that evolutionary demography is what you all do, is what you think evolutionary demography is. And so that we're collectively defining evolutionary demography for ourselves. But let me share a few thoughts that I have about the nature of evolutionary demography. The first thing is that I think evolutionary demography has to build on theory, and a theory is really very, very important. And as Tulja has said, sometimes biologists don't take theory seriously enough, and I think we have to take theory very seriously. So we start with theory. And if we're really serious about theory, then we have to develop models, and usually mathematical models that make the theory precise. So a lot of the work that people in this room do is to develop mathematical models that mathematize the theory and make it precise enough that you can test the theories. And we'll hear quite a lot about that over the course of the next couple of days. Then we have to develop methods and measures, and there's going to be 3 workshops at the end of this meeting on Thursday and Friday. Hal Caswell's giving one on sensitivity analysis. That's a very important set of methods in evolutionary demography. And then there'll be a workshop on IPM models, and there'll be a 3rd workshop on BASTA. I'll talk about BASTA in a minute, but there'll be 3 workshops on methods at the end of this meeting. And we also have to develop measures to study the demography, across the tree of life. And then we need databases. And that's been one of the real achievements, maybe the major achievement of members of society today, and that is to develop the databases that we can use for comparative analysis. And in particular, we have Compadre, plant matrix database. And I just talked with Roberto, who's taking the lead on developing this, but a number of people in this room have made major contributions. And there are almost 1,000 species available in this database. And then there's Compadre, the animal matrix database, and there are 1,200 species in that database. So 2,200 species, really an amazing achievement. And this should enable this group to do a lot of comparative work to study demography across the tree of life. And then Alex Scheuerlein, who's ill and therefore couldn't attend, he's been working for the last several years on DAT-Life, the demography of aging across the tree of life database. And he told me the other day that he had 2,400 species. But there's a different kind of database. And for some species, all he knows is a maximum lifespan. Other species, he has full life tables. But these 3 databases put together should enable lots of comparative work. And then in addition, Dalia Kandi and other people here, under her leadership, are actively assembling data from zoos, and she's made major breakthroughs in getting the International Zoo Association, ISIS, to collaborate. So we're about to get lots of zoo data. And she's also been assembling a lot of field and lab data. Dalia is extremely persuasive, and she is able to call people up. Isn't that right? Yeah. And she's able to call people up and say, give us your data. I know it took you 37 years to gather this data, but share it with us. And she's managed to get a number of people to share really big data sets so that we'll be able to use those data as well. So that's really the foundation of evolutionary demography, all this data. In terms of the methods and measures, I mentioned sensitivity analysis and IPM, but let me highlight BASTA. The reason I want to highlight BASTA, which is the Bayesian survival trajectory analysis, is that it's a method to study mortality, age-specific mortality, when age is unknown. And this is an important issue for many of us in the room because in many cases we observe a group of individuals at some unknown age and then we follow them until death or until we lose track of them. And so how can you estimate demographic functions like the survival function when age at first observation is not known, but you have some data on subsequent observations? Well, so BASTA is a way of doing this, and but there's also a branch of demography where you study life left, life lived and life left. And Jim Carey pioneered this for demographers several years ago, where he came up with the following notion. Suppose you capture a population at some time, and suppose the individuals you capture or mark are a representative sample of the overall population, a random sample of the overall population. But you don't know how old they are. And what you do is you follow them until death. So you observe how many die in the first interval, the second interval, the third interval. Can you use that information to estimate a life table? You don't know the age, but you know time until death. And it turns out you can. So the basic nature of the data are observations of number of deaths, and in the initial period, after 1 unit of time, after 2 units of time, and so on, until the last individual dies after n units of time. So you have this series of death counts by day, or by week, or by year. And from this series of death counts, you can calculate population counts using the extinct generation method. So if you add up all the deaths, you get the size of the original population. And then subtracting deaths, you get the size of the population each subsequent time. So we have data on deaths and data on population size, but not by age, by time since first observation. And how can you use this? Well, what Jim discovered, and which has subsequently been proven rigorously, is that the first formula here, L of x, the life table survivorship function, is equal to d of x divided by d naught. So and remember, L of x is age x, so survivorship at age x is given by the number of deaths, x time periods after observation, divided by the number of deaths in the first initial time period after observation. And of course, when x is 0, d of x is d0, and d0 divided by d0 is 1, so L of x starts with 1 and goes down to 0. Isn't that remarkable? That time until death gives you the survival function? I think this is one of the most remarkable things discovered about life tables. And I've been fascinated by this ever since Jim told me about it. When he told me about it, I said, "Nah, I don't believe that." And then he proved it. So this summer, during my vacation, I spent part of my time amusing myself by thinking more about this. And one of the criticisms that this method has faced is that it only holds for stationary population, for a life table population. And as we know, many populations are not stationary, but they're stable, or they're more or less stable. Demographers use stable population theory a lot. So what I did is I generalized the formula to stable populations. And that's the second formula here. So that you have to correct the formula by little r, which is the population growth rate, multiplied by the number of individuals alive, either x or 0. So a very simple generalization lets you add this method to stable populations. And you can estimate the growth rate if you have observations in 2 periods of time. So I'm hoping that Fernando Colchero, who developed BASTA, and his colleagues will not only use Bayesian analysis, but will also use stable population theory and observations on time until death, as well as distributions of unknown age, to improve BASTA and create more powerful method for estimating life tables. Okay, then also in terms of methods and measures, one of the most important conceptual developments in evolutionary demography has been Annette Bowdish's distinction between pace and shape. And we need measures of pace and measures of shape. So what's pace? Well, pace is the duration of life. Is life slow or fast? And you can measure pace by life expectancy, by maximum age, by age at sexual maturity, reproductive maturity, by generation time. There's different measures of the pace of life. And it's the pace of life in days, in weeks, in months, in years, and centuries. And then, in addition to pace, there's shape. And shape, first of all, pertains to, let's take mortality as an example. Does mortality go up with age after maturity? Or is it more or less constant with age after maturity? Or does it go down with age after maturity? So, do you have positive or negative senescence? And if mortality, for example, goes up, how sharply does it go up? Does it go up gradually, or does it go up very sharply? Well, maybe it goes up and comes down again. There's lots of possibilities, and we need measures of shape to determine whether we have positive or negative senescence or negligible senescence, and then what the sharpness of the senescence is. And this year is the 100th anniversary of Nathan Keith's death. No, it's not. It's the 100th anniversary of Nathan Keith's birth. He died a few years ago, and so there was a celebration in June about this. And so I thought it was appropriate to talk a couple minutes about Keith's entropy, which turns out to be one of several very good measures of shape. And Annette Bowdish's group is looking at entropy plus other possible measures of shape. So let me tell you about some of the remarkable properties of this versatile measure called entropy. First, I'm going to call entropy H bar. I'll explain in a second why. This is the definition that Keith gave. Those of you who've studied entropy, this is familiar. Those of you who haven't studied entropy may look kind of weird, but it was developed by information theorists as a measure of variability and dispersion. It's a little bit like variance or the coefficient of variation. It turns out that L of x divided by the integral of L of x is C of x, the age composition of the population. So C of x is what proportion of individuals are at each age. And so the integral of C of x, H of x, is the average value of H of x. And H of x is the cumulative hazard, the negative of the log of survival. So the cumulative hazard. So I use H bar to denote entropy because H bar is the average cumulative hazard in the population. And then a number of years ago, Noreen Goldman and I independently discovered, and it turned out we were scooped by Mitzvah several years earlier, that H bar can be expressed by this formula. And if you look at the numerator, E of x is remaining life expectancy at age x, and D of x is the probability density function of deaths, so what percentage of deaths occur at each age. Non-demographers hate D of x, because of this D of x, dx, and so on, but they call it f of x, but let's call it D of x. So that the probability density function of age of death. So E of x, D of x, the integral of that, that's the average remaining life expectancy lost due to death. And it's sometimes called E dagger. So it's how much life expectancy is lost because of death. So H bar, entropy, is the proportion, and the numerator here, the integral of the L is that's just life expectancy. So H bar is the proportion, how big E dagger is compared to E naught. How much life is lost to death compared to how much life is lived in terms of life expectancy. So, and this is clearly a measure of shape, because if everybody died at the same time, there'd be no life expectancy lost due to death. If people or individuals died at very different times, there's lots of life expectancy lost due to death. And then it turned out that you can also show that H bar is 1 plus E dot bar. Now, E dot is the change in life expectancy with age. So for humans, how fast does life expectancy fall off, remaining life expectancy fall off with age? It doesn't go down 1 year per year, almost, for younger people. And so E dot is negative for most species that have positive senescence because life expectancy is going down with age. And E dot bar is the average for the individuals of how fast life expectancy is going down with age. So clearly H bar is a measure of shape, because E dot bar is a measure of shape, how fast life expectancy is changing with age. And then finally, you can express H bar in terms of this formula. So which means the first term, the dE dy over E term, that is how much life expectancy is changing over time. Y is time. So for humans, how much is life expectancy growing over time as a percentage of life expectancy, the relative change in life expectancy over time. That quantity, the relative change in life expectancy over time, is equal to H bar times rho bar, and rho bar is the average rate of progress. So suppose entropy is 0.1, and suppose we're making 1% progress every year in bringing death rates down. Then life expectancy is only going up by 0.1% each year at a rate of 0.1%. If H bar were 0.5 and we were making 2% progress, then life expectancy would be going up by 1% every year at a rate of 1%. So H bar is also a measure that mediates the progress in bringing death rates down and the progress in improving life expectancy. So it's really a remarkable measure that can, among other things, be used to study shape. Okay, so here's the three shapes of mortality. So for humans, mortality goes up, and for hydra, mortality is constant, and for tortoises, mortality goes down. And I'll show you some other pictures in a minute. And one of the basic things that evolutionary demographers have to worry about in terms of theory is why does mortality go up with age for some species and this level with age for other species, and goes down with age for still other species. And Tom Kirkwood is here, and he developed the disposable soma theory, which explains why mortality goes up with age for species that segregate the soma from the germline. And but species that don't segregate the soma from the germline, like hydra, are different. And the tortoises, which keep on growing, may be different too because of indeterminate growth. So we have to expand Tom's theory to cover the whole spectrum of possibilities. But Tom's theory explains the increase in aging for a large number of species. And so we've been looking at different species. And one of the species we've been most carefully studying is hydra. Here's a picture of a hydra, very cute little sac. And hydra don't age. Mortality is constant. This is work that was started by Daniel Martinez, who's here. And he showed that mortality is flat. And we've replicated this, and he's extended his work, and it really is flat. And fertility is also flat. So there's no aging. The hydra maintain themselves. And a very important question is, why do hydra maintain themselves? What's the evolutionary basis for this? And here's a hydra in the context of three other species. The C. elegans, the worm studied by gerontologists interested in aging, and then the mute swan, hydra, and a plant. The tortoise looks something like this plant picture as well. And for the C. elegans, this little nematode worm, fertility, the blue line, falls sharply after sexual maturity, and the red line, mortality, rises after sexual maturity, and the gray area is the survival curve, and you can see survival going down. And we start the, I don't know if you can see it in the back of the room, but we start the diagram at age 4, which is age of sexual maturity, and we end the diagram at age 25, which is the age where 95% of adults are dead, and only 5% are still around. And the C. elegans is the only species that satisfies the traditional evolutionary theories of aging developed by Medawar, Williams, and Hamilton, who predicted that mortality should rise starting at sexual maturity, and fertility should fall starting at sexual maturity. This is the only species that meets the theory. Then there's mute swans, which were object of a major study, and to try to find senescence, and eventually at the very end of life, when hardly any individual is still alive, there is some rise in mortality and fall in fertility, but over the bulk of life, it's pretty flat. And for hydra, it's very flat, extremely flat. So there's a sharply falling red and blue line at the beginning when the hydra adapt to laboratory conditions, and then there's an absolutely flat line. And again, I don't know if you can read it, but the age at which 95% of hydra would be dead, at the age of which only 5% would still be alive under laboratory conditions, is 1,417 years. So the hydra is not only flat, but it's very, very long, extremely long. And then finally, for this desert plant, mortality falls with age as the plant gets bigger and fertility goes up. So here are, let me go back. These diagrams and the next ones I'm going to show you are in an article called Varieties of Aging Across the Tree of Life. And a number of people in this room have contributed to this. And Owen Jones is the first author. These are the 6 main authors, but there's also other co-authors. And Owen found out last week that Nature was going to publish this as an article, not as a letter, but as an article. So this is going to be a major event for evolutionary demography. And in this article, there's a figure that shows 46 different species, 3 grass for humans and 45 other species. And the first diagram here is like the hydra diagram I just showed you, but the red being mortality, the blue fertility, and the gray area the survivorship curve. This is for Japanese women today. And you can see this really sharp increase in mortality with age on this age standardized scale, where we go from maturity to 5% survival. And then the second diagram is Swedes born a century ago. And the fifth diagram are hunter-gatherers, some data from hunter-gatherers. But in between the hunter-gatherers and the Swedes, we have a bird and we have a guppy. And then we have another bird at the end of this group. And and here's a few more species. And you can see this remarkable variety of patterns where mortality for these species is generally going up, but at the bottom, we ordered them according to how much mortality went up with age. At the bottom, mortality is not going up very much at all. And fertility is showing very different patterns, sometimes falling, sometimes rising with age. And then finally, the last few species, we have the mortality and fertility are very flat, or sometimes mortality is flat and fertility is rising, and sometimes at the very end, mortality is falling and fertility is rising. So there's this great variety of patterns across the tree of life. And a number of people here are really interested in this and trying to explain why we have this kind of variety across the tree of life. So I think this is a really important topic for evolutionary demography. Now, in terms of modeling, I just want to make one remark. Very often in demography, we use this formula. Mu of x is the force of mortality, the chance of death at age x, which is A e to the bx, that's Gompertz's law, plus C, that's Macon's addendum. And this seems to fit fairly well for a number of different species, and sometimes C is important, sometimes C is close to 0. But for many species, it turns out that mortality not only depends on age, but depends on stage. I just wanted to give one simple example of this, but I know several people in the room are working on combining both age and stage data in the same model to try to study mortality and fertility. So suppose W is some measure of size, like weight. Then mortality might be going up with age, but might be going down with size, because its predation maybe is less of a threat for bigger crocodiles than for smaller crocodiles. So then you'd have a combined model with one force going up, the other force coming down, and you can get a situation where mortality falls for a while and then starts to rise at the end because of these two opposing factors. And I think a very important next step for evolutionary demography is to try to combine age and stage into the information in the same model. Here are humans, and it's really remarkable how steep the rise in mortality is for humans. The average, we standardize things so that the average force of adult mortality is 1. So if you take total number of adult deaths and divide it by the total number of adults, that's the adult force of mortality. We standardize that at 1. And then we look at the ratio of the force of mortality to other ages to the average adult level. And at age 100, the force of mortality is more than 20 times higher than it is on average. And for a long time, all the way up to age 80 or so, 70 or 80, the force of mortality is less than 1, and then it rises very, very rapidly in old age. And we need to try to get a better understanding of why humans have this enormously sharp aging. We're really outliers compared to other species in terms of the steepness of the aging trajectory. And one way to look at that is to compare humans with modern humans with hunter-gatherers. So here, Oscar Burger, Annette Badish, and I, we looked at mortality for a group of hunter-gatherers, and the curve for mortality is given in red, and you can see it's not a different scale and so on, but it's not as steep as the modern curve. And then the dotted red line is the level of lowest mortality. And you can see from age 10 or so up until age 30 or so, it's really pretty level. It's a little bit more than 1% per year. So pretty high level. And then falls rapidly in early childhood and then rises after age 40. For some of the hunter-gatherers, the lowest level of mortality is reached around age 30 or 35. It takes a lot of learning to get to be a reasonable hunter-gatherer who can find food and take care of himself or herself. So that because of this learning, mortality is very flat for a long time. So over time, mortality has come down. So this is Sweden in 10-year intervals from 1750. And you can see in 1750, the top blue curve is not that different from hunter-gatherers. And then there was a period of time where it didn't change very much in later childhood, but it was changing rapidly in early childhood, and then infancy. And then you can see the curve on the bottom, which is the most recent Swedish curve in 2010. And this is on a log scale, so it's just an enormous difference, a factor of 100 or more between the level of mortality today at younger ages and the level of mortality for the hunter-gatherers. Just an enormous difference. And even at older ages, there's a big difference. This is on a log scale, so it doesn't look so big, but if you put it on an absolute scale, it's very, very large. And if you look at the lowest mortality across the lifespan, then the hunter-gatherers is the black line, and in some era, different hunter-gatherers have different levels, so those are the two dotted lines. And then we have chimpanzees, the green line, and acculturated hunter-gatherers who get some medicine, food from modern civilization. And then Sweden in blue, France in gray, and Japan in red. So you can see there was not very much difference between the Swedes and the French and the acculturated hunter-gatherers, and then an enormous decline starting around 1850 or 1900. And you can also see that the modern humans at the end of the... can you see the slides still? Not that well. Maybe you can see this sun in Denmark, very rare in this time of year. At the very end, you can see that the modern humans in Sweden, France, and Japan are just vastly lower than the hunter-gatherers, and the chimpanzees are closer to the hunter-gatherers than we are to the hunter-gatherers. So in 150 years, we've moved further in terms of mortality than we did in 6.6 million years from the time chimpanzees and humans separated. So a lot of what's happening to humans is not genetic. There's very little genetic change in 150 years. Almost all of this is due to environmental change and behavioral change. This brings me to the linear rise in best practice life expectancy. So we studied the countries that are doing best in terms of life expectancy, and those are the dots that are along the straight line, and then looked at several different countries compared to the linear rise. The country doing best in 1840 was Sweden, Swedish females, and then Norwegians, and then people from New Zealand, and recently people from Japan. And there's a very, very close to a linear increase in the best practice with a record life expectancy. And the various other countries, you can see from the diagram, caught up and then fell behind. So for any particular country, it's a more erratic pattern, but there's been a steady long-term revolution in life expectancy. And this has resulted in an absolute explosion of centenarians recently. So just to show you how much things are changing, I don't know if you've ever seen graphs like this, where nothing happens and then it goes straight up. So there were no Swedish centenarians for most years in the 1800s, and no Japanese supercentenarians, 105 plus, until 1975, and then this extremely rapid increase. So, how do we explain the revolution in human life expectancy? And I think this is one of the big puzzles for evolutionary demographers. And one thing we've come up with, and this is something that Tulge has also been working on, is what's the relationship between life expectancy and life disparity. So life disparity can be measured in a number of different ways, but basically how different are the ages at which people die? How different are people's lifespans? That's life disparity. And life expectancy is how long do people live on average. And we have a measure of life disparity, which is this E-dagger measure I was telling you about before, the average number of life years lost due to death, or more precisely the average remaining life expectancy lost due to death. And you can see, just take Italy for example, life expectancy is 83.7 for women and 78.2 for men. When a woman dies, on average, she loses 9 years of remaining life expectancy, and when a man dies, he loses on average 10.3 years of remaining life expectancy. And just to put it in comparison, the probability of death before age 65 is 7% for women and 14% for men. And if you run down this diagram, you can see that as life expectancy goes down from Switzerland to Russia, life disparity goes up, and the probability of early death goes up. And there's actually a very strong relationship between life expectancy and life disparity. The horizontal axis is years below highest life expectancy, and the vertical axis is years above lowest life disparity. We have data for 160 years for a number of different countries. 89 points out of the 160 points are at 0-0. So 89 cases out of 160 cases, the country with the lowest life disparity had the longest life expectancy. And in most cases, countries with the lowest life disparity have something close to the highest life expectancy. There's a very strong relationship. So the main way that life expectancy is increased is that life disparity is reduced. And life disparity is reduced by averting early deaths, by averting deaths before life expectancy, because you avert death after life expectancy, you increase life disparity. So the countries that have made progress are the countries that have reduced life disparity and thereby increased life expectancy. If you look at the human data more carefully, and the data I showed you before only go up to the age at which only 5% of adults are still alive, which for the Japanese female, by the way, was age 102. But in any case, if you keep on going up, and if you don't put it on an absolute scale but on a log scale, you get a picture that looks something like this, where there's a possibility that human mortality may level off after age 110. So we've done a lot of work on trying to get data on supercentenarians, very, very old people, and to see whether mortality actually does level off or not for humans after 110. You know, despite this very, very rapid rise at earlier ages. And it turns out that human life expectancy does level off at the highest ages. And so the good news is if you survive to 110, your chance of death no longer goes up. But it's 50% per year. and it's an artifact of changing composition. So of course, if you study very, very old people, meet them one year, meet them a couple of years later, they're sick or they're frail, or their chance of death is obviously higher. So the reason human mortality appears to be flat is because of selection in the heterogeneous population. The frail die first, making the remaining population more robust, but these more robust people get to be a year older, making them frailer, and these two forces exactly balance out. So the human mortality data are consistent with this first model. It turns out that a number of people, including Ken Wachter and Trifon Missoff and others, have studied this leveling off. And if you have a population is broken up into groups, and each of the groups has exponentially increasing mortality, the vertical axis is on a log scale, so the straight lines are vertically increasing. And the group with the highest level of mortality is dying out the quickest, so that's why the blue is fading away, because they're dying out. And those groups with the lowest mortality are becoming more and more important in terms of the percentage of the survivors. If you have a situation like that where everybody's aging exponentially, but there's heterogeneity, then you wind up with something like the red curve with this leveling off. You can prove this mathematically. If, on the other hand, some individuals are aging faster than others, then you wind up with the other red curve where mortality goes up and then comes down. So it's pretty clear that for humans, the rate of aging is the same for everybody, but people are at different levels or mortality. But for other species, it may be that the rate of aging is different for individuals, and some individuals are aging more rapidly than others. We've been spending a lot of time and effort trying to figure out what the rate of aging is for humans, and we think, it's still a hypothesis, it's 14% per year. Everybody in this room, your chance of senescent death, not accidental death, but senescent death, is going up by 14% per year. Doubling every 5 years. Luckily, from almost everybody in this room, it's low still. But when it doubles every 5 years, it gets to be pretty important by the time you get to be 80. Okay, so let me conclude. It seems to me that evolutionary demography has to be based on theory. We should take theory seriously, and to do that, we have to develop models that make the theory precise. We need methods and measures, and there's a lot of work being done on this by people here in this room. We need measures on, we need better databases, and there's been enormous progress over the last couple of years in terms of databases that will be freely available to everybody who wants to use them. And this is already beginning to lead to findings in major journals, and I think it's going to be an explosion of findings over the next few years. So, let me conclude by making the following remarks. Humans are outliers. In fact, I was studying the comparative demography of aging. I was surprised how far we are as outliers. We're just vastly different from other species, and we've become even more different in the last 150 years because of non-genetic change. And when you think about humans as outliers, you can think about the fact that humans organize this conference. And only humans are making presentations. And so humans really are very different from other species. But nonetheless, as Jim Carey has emphasized, by studying many species across the tree of life, we may be able to come up with some fundamental relationships that let us understand the species better. There may be some deep underlying concepts that tie different species together. And by looking at the comparative biology of the demography of different species, we may be able to uncover some of these fundamental relationships. One, as I mentioned before, is what's the distinction between shape and pace. And it appears that these two, shape and pace, are orthogonal to each other. They're two independent ways of thinking about life. And then you can try to study what determines the pace of life and what determines the shape of life. Dobzhansky said that nothing in biology can be understood except in the light of evolution. But what drives evolution? Evolution is driven by birth and death processes, by population growth, population decline. So it's equally fair to say nothing in evolution can be understood except in the light of demography. And so I see demography as the way forward. It's a way to make real progress in understanding evolution. And the pendulum of biology has swung so that in most biology departments, including one here, 80 or 90% of the people are doing molecular biology. And a lot of the work is non-theoretical. But biology basically, as Dobzhansky argued, biology basically is about evolution. And I think the pendulum is going to swing back. There's going to be much more attention to ecology and evolution in the future. And as the pendulum swings back and as ecology and evolution become more important, I see demography as a way forward, because nothing in evolution makes sense except in the light of demography. Thank you very much.
We have time for some questions.
Yeah, unfortunately, we had a cancellation for the next session, Alex. For a session tomorrow, so we're going to shorten. We only have 2 presentations in the next session instead of 3. So there's a little bit of time for questions right now. Cliff?
Over the last 9 years, we've talked a lot about the shape of trajectories, especially since you're in Annette's paper. And I've always been especially interested in the tail of the distribution, and Jim Carey has talked about this a lot. As an empiricist, when I have yet to find a model that I've applied to any data where it's not really dramatically influenced by the early stages of the trajectory, and much less so at the end. So I think that one of the frustrations I've had is interaction between the people collecting the data and those developing models, because I don't know of a model that goes up and then actually will go down.
Oh yeah,
with empirical data that's been collected.
So
in theory, it should.
The problem, Cliff, as you know, the problem is you have to study an enormous number of individuals to get enough data on the oldest ones. Suppose you're interested in our forthcoming Nature paper, we stopped the analysis at the age when only 5% of adults are still alive. So if you're studying 1,000 adults, we stopped at when only 1/20th of that 1,000, only 50 were still alive.
Well,
but you need an enormous study.
A theoretician will always tell the empiricist that the problem is that your data. But the fact is that
it's not your data.
I can invent data sets that are should do it, and they still don't.
No.
They don't behave the way they should.
The problem is that if you want to study the final 1% of life, you need an enormous number of individuals to have enough of the final 1% of life. And you have to have accurate data too. So let me just give you an analogy from humans. We were interested in knowing whether or not human mortality leveled off after age 110. There are billions of people in the world, 7 billion people. How many people are above 110? A few hundred. And it took an enormous effort for us to find these few hundred people. And most of them were liars. Overwhelmingly. I mean, if somebody says they're 112, either they're senile and their kids don't know how old they were, or they're liars. And so you have to get birth records, and you have to make sure that this person really is the person to whom the birth record pertains, and so on. So it took a colossal amount of work. It took 10 years of effort from a bunch of people in order to get some validated information on the very end of life. And that enabled us to show that mortality is flat. Well, mortality is flat from 110 to 114. We don't know after 114, right? Because there's so few observations. So that's just the fact of life. If you want to study the tail, you need very big studies. Careful studies. Better studies. Okay.
Jim, that was a great talk. When you presented the slide and the discussion about life expectancy and life disparity, it sort of started me thinking about a topic that's been much discussed recently, which is social gradients in human populations and variation in position within the societal pecking order. And I just wonder whether in any of the work you've done on the patterns across the tree of life, whether you have looked or anyone has looked at to the extent to which those patterns are influenced by the presence of social structuring within populations. Because where you have social hierarchies, pecking orders, that will generate automatically a degree of heterogeneity, and those that are lowest are likely to die soonest. And it could be an interesting second-order effect on the pattern. I don't know whether...
No, actually, there's been quite a lot of work done on this, and Ryan Edwards and Tolja have done work on this, and Sir Michael Mormont in England has headed up the Whitehall study, and they've done a lot. And there's other studies like that. And the U.S. National Institute on Aging, Richard Sussman's branch, is organizing a workshop on sociality and senescence next spring. So there'll be proceedings from that conference.
Sociality and senescence across other species.
Yeah, so
humans are familiar.
Yeah, so they're going to. So I was asked to participate in this conference, and I said no, and then they leaned on me, and I said yes, you know how it is. And so and they wanted other species, not just humans, but other species too. So I agreed to write a paper about social solidarity and senescence, not only for humans but for other species. But I don't know much about sociality in other species. So I've been trying to learn something about it. And humans really are outliers. We're much, much more social. There's social species, of course, but in terms of, for example, if a child's in a hunter-gatherer society, if a child's mother dies, or father dies, the other people take over, even though they may not be genetically related to the child, which is rare in other species. And there's other degrees of sharing sharing of food and sharing of resources among humans, which are in the order of magnitude more than other species. So it's not clear how much we're going to learn, but I decided to look at social solidarity across the tree of life. So how would you measure social solidarity? Well, I decided to measure it in terms of life disparities, so that the species has a high degree of social solidarity if individuals die roughly at the same time, and they have a lack of social solidarity if individuals die at very different times. So crocodiles are not very social in terms of this measure, and humans are highly social. So, make sense? Yeah. So, I'm able to write this paper without using any data at all, because entropy is a very good measure of disparity of lifespans. And entropy is also a very good measure of the steepness of the senescence curve. So, by definition, in some sense, the same measure that measures social solidarity measures the steepness of the mortality curve. So the two have to be very closely related. But I'll get some data too. But anybody in here who has some thoughts or comments about this, please tell me. I've been warned that I'm going to be very embarrassed at this meeting when it takes place, and because there'll be people in the audience who know a lot more about sociality than I do. So if you have some clues about how to study sociality across the life course and answer Tom's question, I'd be very interested.
We should probably say thank you, Jim.
Okay.
And their coffee break.